Okay, welcome to the second video. Um, so carrying on, number 12 says list the distinguishing characteristics of each of the following atomic models. So we've got Thomson's, Rutherford's, Bohr's, and the electron cloud. I could talk for a long time about this because it kind of starts getting into physics, and physics 30 is when you'll start learning more in depth about these things. But Thomson's plum pudding model, really shortly, he discovered that the electron or that the atom had a positive aspect to it and a negative aspect to it, and he figured that it's also called the raisin bun model, which might make a bit more sense to you because I think a lot of people don't know what plum pudding is. But the raisin bun model means that we've got the bun part of it would be all positive, and it has these negative raisins that are kind of sprinkled into it. So kind of like food, I guess. So just if you can remember that. So that's Thomson's model. He just knew that there was negative things and there was positive things, but he wasn't too sure about the way that they were organized. Moving on to Rutherford's model, or the planetary model. And actually, these pictures are kind of mixed up because Rutherford's picture actually would have looked more like that. That's kind of the typical Rutherford picture that we have. And what he thought, both these pictures work. This just doesn't really show the Bohr model very well. So Rutherford's model, or planetary model, he figured that there was all these negative negative things, these electrons, that are orbiting around this center positive thing. Which made a lot of sense too, and actually as a kid I thought this made a lot of sense because this is just like what the planets do. It just seems like, well, if I get even smaller, we've got like the same type of thing happening at the very small level as we do at the very big level with the solar system. So that's kind of what he thought. That's probably all I'll say about that. The Bohr atomic model, probably a better picture, was the one where we had, I don't know, the one that's on our website too, where you can have that build an atom simulator. So with that one, we have, let's say, like helium would have neutrons, those are ends, orbited by two electrons, right? So that's the Bohr model. And he said that, let's say we gave this helium atom some energy, well, that electron would jump up from one energy level to the next energy level. But the cool thing about this is that he said it would be nowhere in between. So that electron would actually really transport from this spot to that spot and be nowhere in between in that space. So really teleport. He thought that that electron must teleport, which all sounds crazy, but it's really based on a lot of evidence. If you take Physics 30, we'll talk about what that evidence is. And then finally, the electron cloud gets even weirder, and it says that actually the electron that we thought was orbiting this proton, or these protons at the center, the nucleus, apparently this electron is actually just a wave. So not a particle that we thought was, zipping around the outside of this thing, but it's actually a wave, like a water wave. And it's just this fuzzy kind of cloud all the way around the outside that we might find an electron there, or we might find it there or there, and it's very strange. And there's no getting around the fact that it's very strange. But if you guys want to talk more about that, because I find it really cool, come find me. All right, what is an element? Provide an example. So an element is something like helium, like I was just dealing with, I guess. And it's made up of a bunch of different helium atoms. So you got a whole bunch of helium atoms, you've got an element. So we've got our periodic table of elements. Yeah, so provide whatever example you like. So moving on. So define each of the following components of an atom. So I'll just draw a picture of an atom. So we've got a proton. Let's do helium again. We got a proton, neutron, and two electrons. So define each of the following components of an atom. So the protons are in the center. They are positive. So protons are positive. Neutrons are, the name comes from neutral, it means they don't even have a charge, so no charge. And then we've got electrons, and they are the negative things that are zipping around the outside. unless we look at the current model, which says these are actually like a weird wave thing. So, but it's easier for us to, in chemistry, to think about these things as being little particles zipping around the outside. What does the atomic number of an element tell us about a neutral atom of that element? Okay, so I found a picture online to kind of help clarify this. The atomic number, or proton number, really means the amount of protons, right? So the atomic number is telling us how many protons there are in that atom. And since we said it's neutral, protons are positive, right? That means I also know how many electrons there are. There's also 2. There has to be 2. If I've got 2 positive things, it needs to have 2 negative things to balance it out. The atomic mass differs, where the atomic mass is the number of protons plus the number of neutrons. So if I know the atomic mass, I also know that there's 2 neutrons in this one, because 2 protons plus 2 more neutrons must equal 4 for the atomic mass. And the reason, you might ask why we've got like 0.003, and the reason for that is because we got better at measuring the mass of protons and neutrons after. So we originally had that number off a bit, so we kept that original unit for mass. So because of that, we've got these extra decimals. It's just kind of a, yeah. What we're going to do for all of these, though, is just like round. So round that to 4. Pretend that's 4. And that's good enough for us. Okay. Okay, so this one says, using your periodic table, draw an atom of fluorine. Recall that the first orbital of any atom may contain up to 2 electrons, and any subsequent orbitals may contain up to 8. How would an atom of fluorine differ from an ion of fluoride with a charge of -1? So first off, if you're looking at an atom, so that just means it's like neutral, right, of fluorine, the atomic number for fluorine, where'd it go? Periodic table, is 9, right? So we got 9 right there. That means that there's 9 protons. So in your picture, you should have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. The other thing that we can tell from the periodic table is that it says our atomic mass is 18.9, yada yada. So really 19. So we know how many neutrons there are, because the number of protons and neutrons have to add up to 19. So I know that 9 plus 10 neutrons must equal that. So there must be 10 neutrons. So at the center of this, you should also have, so let me get my pen. 4, 5, 6, 7, 8, 9, 10 neutrons. Blue ones are neutrons. And then we're going to have the first orbital, you're going to have 2 electrons. And then the next orbital, you'd have 1, 2, 3, 4, 5, 6. So in total, the electrons, I've got 9 electrons around the outside, right? So this one wants to have 1 more electron to complete its next shell. So there's only 2 electrons allowed in the first shell or orbital, and 8 allowed in the next one. A fluoride ion would have just 1 more electron. It actually stole an electron from somewhere else to fill its outside shell, so now it has 8 electrons. Remember, they have a charge of negative and -1, right? Just each electron has a charge of -1. So since it gained 1 more electron, it now has a charge of -1. So that's how it would differ. It stole an electron from something else. Yeah. So 17, who first developed the periodic table? Why was this such a great achievement in the field of science? This was this guy, right? Dmitri Mendeleev. It was such a great achievement in the field of science because he was able to actually predict where certain atoms would actually be. So he said that there must be some atom that we just haven't found yet, or certain elements that we just haven't actually found yet. And then they actually did find those later. So it was a great achievement because we really understood the way the atom must actually work too. The way that that matter itself works, it does follow an organized pattern, which made it so we could actually interpret that pattern. We could see that pattern. We could start to make predictions from that. So it was a really big achievement in the field of science. All right, moving on to 18. Which group of elements is the most reactive, and which one is the least reactive? So the most reactive group of elements, I'll get a periodic table here, is going to be this one, the alkaline earths, the alkaline metals group. It has one extra electron, and it wants desperately to get rid of that extra electron, which makes it very reactive. The least reactive group is actually all the way on the other side, our noble gases. They have a complete outside shell, whether that's the first orbital with 2 or the second orbital with 8, because 2 plus 8 would be 10, right? 10 electrons. It's happy. It's noble in the fact that, or in the sense that it doesn't want to hang out with the other riffraff, right? It's like nobility. So the noble gases are the least reactive. Okay, 19. So complete the following chart comparing metals, nonmetals, and metalloids. State at room temperature. For the most part, metals are going to be solid, except for the exception of mercury. But for the most part, solid. Non-metals, they can be really anything. Noble gases are obviously gases, but we also have carbon and stuff that are solids. Yeah, so they can actually, and bromines in there too, so it can also be a liquid. Metalloids are all solids at room temperature. Though, and remember, metalloids, just if you can't remember, metals are going to be everything to the left of the staircase, this being the staircase. Non-metals, everything to the right of the staircase, and the metalloids are actually the ones that kind of follow the staircase down. So yeah, so the ones that, yeah. Appearance, metals are shiny, just like you think of like a sword or something, right? Metals are shiny. Non-metals are, we could say, dull. They're not very shiny at all. And metalloids too are usually, they're like a dull or maybe shiny color. They don't really know which one they want to be. Conductivity, metals, like you think of like copper wire, are very conductive. Non-metals, if you have a piece of carbon, it doesn't conduct electricity very well. Or if you have a hydrogen, it doesn't conduct electricity very well. Metalloids, this is why they're so good for computers, is they don't know whether they want to be conductive or not, and we take advantage of that to make computer chips. Malleability, metals are malleable. We can hammer them into swords. I keep talking about swords, but I don't know. We can hammer them into stuff. Ductility, which means like the ability to stretch into a wire. Metal, we can do that with metals, right? We can make it a necklace if we wanted to. Non-metals, neither of those things. They're not malleable. They're not ductile. Metalloids, yeah, they're, again, don't really know how they want to be. Okay, moving on to the next one. Okay, oh, my pen stopped working. 1 minute. Okay, I think I got it. For each of the following compounds, list the names of elements of the elements present, how many atoms of each element are present, and the state of matter the compound is found in. So if we look at water here, we've got names of the elements. We've got hydrogen is the H, oxygen is the O, and we've got 2 atoms of hydrogen and only 1 atom of oxygen. And this G in brackets behind it means it's in a state, it's in a gaseous state, so it's a gas. The next one, we've got 1 carbon, we've got 2 oxygen, and it's in a gaseous state. We've got 2 atoms of iron. We've got 3 atoms of oxygen, and it's in a solid state. We've got, so D, we've got 1 atom of hydrogen, 1 atom of chlorine, and that's an L in brackets, which means it's a liquid. Okay, so for 21, I'm going to start with the ionic compound. So this is going to be an ionic bond, is what they have. So with an ionic compound, if you think about sodium, what I've drawn here is I've got sodium chloride, so it's an ionic compound. And sodium has 1 extra electron in its outside shell. everything in this column in the alkaline earth or alkaline metals has one electron in its outside shell. So it's got one to give. It wants to get rid of it. Chlorine, on the other hand, is lacking one. It's got in its outside shell, it's got 7. It wants to have 8, so it desperately wants an electron. So what happens in the ionic bond is sodium gives that electron to chlorine. Now they're both happy, right? But what also happens when they give that electron is now, remember electrons are negative, right? So sodium gave something negative away. So now sodium overall is positive. Chlorine has gained something negative. It's gained that negative electron coming over here, right? So now overall, chlorine is negative. Negative and positive things attract each other. So that's why negative and sodium and chlorine now attract to each other. So that's really what an ionic bond is. It's just a positive thing, this sodium, attracting this negative thing, this chlorine. It all had to do with giving that electron to the chlorine atom. So that's ionic bonds. So ionic compounds are formed between metal, so everything, I can't write on this, everything on the left side of the staircase, all the metals over here, and non-metals. So it's gonna so it's gonna be sodium and chlorine. So metal, non-metal. Okay, molecular compounds, on the other hand, they deal with either molecular bonds, you might hear it called, or you might hear it's called a covalent bond. That's really the same thing. So molecular compounds, they share their electrons. So what happens if we look at oxygen, like this is H2O we're looking at, H2O. We've got oxygen, and in its outside shell, I represented with dots, right? It has 6 electrons in its outside shell. So it needs 2 more electrons to complete its outside shell. So what happens is hydrogen, it only has 1 electron, so it has 1 in its outside shell. It wants to have 2, right? Hydrogen wants to have 2 to complete that first shell. So hydrogen wants 2. Oxygen wants, this hydrogen wants 1 more electron. So what's going to happen is they're just going to share. They're just going to share these electrons. So they share those together. You can't really say one has the other and the other one doesn't. They just kind of both hold on to it. So molecular compounds, they share their electrons. And just before I forget, that should be green. Molecular compounds are made of non-metals, so everything on this side. So that being said, you might notice that hydrogen was the example I used. Hydrogen is that one kind of oddball that could be in both places. Hydrogen could really be sitting right there too. Yeah. And I'm noticing this video is getting too long, so I'm going to make a part 3 of the video. So see you in the next one.